Okay, we're gonna start doing exam for review part 1. So our first question is gonna be provide a mechanism for the following reaction. These are the diazonium salts and nitrosium amines, nitrosamines that you have to be worried about. So I believe that on your test, the only things that you're gonna be tested on for mechanisms are gonna be the things with amines. And this mechanism, it was on my test. It was one of the longer mechanisms, so I knew the answer. These answers are easy, like to know the product for it, but the mechanism is kind of crazy. So remember, if you don't know the mechanism, at least write the product, because that's already half of the points for your reaction. So primary, I'm going to give you a little chart just to know your products. So for primary amines, you get diazonium salts, and for secondary, you get N-nitrosamines. Okay, so now let me provide you with the mechanism. So right now, I'm working with a primary amine right here. So I know that in my products, I'm going to have a diazonium salt. Diazonium salt. And let me show you what a general diazonium salt looks like. Remember, it's a salt. So like if you think of table salt, NaCl, there are two ions together. So when you think of diazonium salts, think of the ion. And we had always seen this N2 plus ion and chloride. So this is your salt. For N-nitrosamines, this is a simple N-nitrosamine. Let's see. Yeah, I'll do this. On your nitrogen, on your N, I have a nitrosamine group. A nitro group, I'm sorry. Okay. So then for this one, I'm already going to draw my product so we know that what we're working towards. My diazonium salt, keep all my carbons constant, and I'll just add chlorine to neutralize the charge. Okay, but let's start with the mechanism. So I'm using HCl, and the first thing I'm going to do is, like always, HCl is an acid. It's going to protonate something. So we're starting with our starting products right here. There we go. Yeah. Protonate. Get OH. Cool. We're going to keep protonating. A lot of this is going to be a lot of protonation with HCl. We make a water. Okay, we'll go. Okay. So we made a good leaving group. So leaving group is going to leave. And when the leaving group leaves, we have a charge in our nitrogen. NO. Cool. Finally, we're going to be able to use our amine group in order to make that salt. So amine will be our nucleophile, and the one with the positive charge is going to be our electrophile. Equal to hydrogen. There we go. Okay, so we have a positive charge on our nitrogen. We know that we need to keep that nitrogen so it's not going to become a leaving group or anything. So what we're going to do is we're going to use chlorine, negatively charged chloride group, and we're going to deprotonate one of those hydrogens. Put the electrons back on nitrogen to make a neutral compound. Cool. Yeah. Okay, again, a lot of protonation, so HCl comes back. Pronate. We have positive charge. Okay, so we're trying to get rid of that OH. So we're trying to make it a good leaving group. So what we're gonna do is we're gonna make Cl again. Oops, I put it on the wrong one. A chloride group, come and deprotonate my nitrogen. Put those electrons on my nitrogen bond and neutralize this right here. Space. Let me see if we're good so far. Yeah, it looks good. Nitrogen to one nitrogen. Oxygen bonded to nitrogen. Cool. And so we're going to do one more protonation. We're trying to get rid of that OH. So make it a good leaving group. Use HCl one more time. Oxygen will be your nucleophile this time, or your base. And we made another good leaving group. Oh, hydrogen. Cool. This is your last step. I'm going to put the electrons that are my nitrogen into a triple bond between nitrogen and nitrogen and kick off that leaving group. And I get my diazonium salt. So it's a lot of steps. If you don't want to remember the steps, just know the product, because that's half of the points, and there's a lot of easy points that you can get on this exam. So yeah. Next one that we're going to do is predict the products. Predict the products are a lot easier. So for this thalidomide one, I think that's how you say it. Jared, don't come at me for this. For this thalidomide one, you need to know the mechanism. This one was on my exam as well. And so all that happens here is this is Gabriel's synthesis. Gabriel's. And what Gabriel's does is it makes primary amines. And so the primary amine where the nitrogen will be on your compound is right here, instead of the good leaving group. So OTS, good leaving group. So all you have to do is keep your carbons constant. We usually don't drop any carbons for these nitrogen reactions, amine reactions. And I'm just gonna write my primary amine. That one's not too bad, but again, learn the mechanism for this one. The mechanism, that's a good one. That's a good one to learn. So, okay, so these over here, let me bring this over here. Remember this little chart for yourself so you can do those products easily. So it's the same thing with the diazonium salts and the nitrosamines. Find out whether your amine is primary or secondary. So here I have a primary amine, so I'm going to make a diazonium salt. And then use Cl to neutralize the charge. Okay. For this next one, secondary amine, what I'm going to do is an N-nitrosamine. So again, you keep your nitrogens, keep your carbons, and you're going to put a nitro group on your original nitrogen that was already on your carbon compound here, your amine, secondary amine. Okay. And I made my N-nitrosamine. Okay, cool. For this next one, same thing, primary amine, it's gonna make a diazonium salt. And just substitute that NH2 group with N triple bonded to N, which gives me a positive charge, and chlorine to balance that charge. Okay, cool. And this is going to be important for a lot of the reactions that you have to memorize for this test. Okay, so for this next one, it's Hoffman's. Hoffmann elimination. What you need to know for Hoffmann elimination is that your major product is going to be the least substituted. So major So I would ask your professor if they want you to write both of them and label the major one. But in this one, I'm going to write both of the elimination products and then I'll label. Yeah. Okay. I would say know this mechanism as well for your test. Okay. So your first reaction is just going to make a good leaving group right here instead of this nitrogen group that's not really a good leaving group at all. So it's just going to make it a good leaving group. And the second part provides hydroxide to deprotonate a beta carbon. So this is your alpha. This would be your alpha. And these are your betas. So only between the alpha and the beta bond is where we're going to put the double bond. And so I get two products. Remember, leaving group leaves at one point, so we forget about that. And I get my two products. Keep all your carbons constant. And so this one is least substituted because it only has one group around the double bond, whereas this one is tri-substituted. 3 groups around the double bond. So my least sub in the Hoffmann elimination is going to be my major product. Major. So make sure to see what the question asks or ask your professor if they only want you to write the major product or both products and then label. For the synthesis one, I'm going to show you how I solved my synthesis questions. These are short synthesis, but they show you a lot of the important reactions that you had to learn. So they should be like critical thinking. Okay, so here I'm starting from a secondary alcohol and I'm adding an amine group with a methyl group. And so immediately what I'm thinking is I'm gonna have to do reductive amination. That's what I'm hoping for this one. Reductive amination, because with your reductive amination, you can add whatever R groups and a nitrogen onto your compound. So for my first reaction, I know that it's kind of like when I'm doing amines and imines. So it's that reaction is gonna have to go first. So I'm gonna make my carbonyl using PCC. So first reaction, it's gonna make a carbonyl. My second reaction, I am gonna try to make, well, there's only one carbon, so it would be a primary amine group that I would add. So then I'm gonna make an imine. So using NH2 with a methyl group. And that makes this right here. Cool. So we're one more step closer. Ooh. I can see that the only difference between these two products, this one and this one, is I have a double bond, so use anything to reduce. One of the more popular things that you can use is H2, 2PDC, hydrogenation reaction. And so you reduce your amine group, and this is your whole reductive amination reaction. Yeah. I'm gonna make this smaller. Okay. I'm gonna change my color so I don't get confused. Let's go to this next one. Okay, so I have an amine on my left and I have like a double bond on my right. So I know that we're gonna do an elimination, and one of the elimination reactions that we've learned so far or in these chapters for this test is the Hoffmann elimination. So that's what I'm gonna be going for this one. Hoffmann. elimination. And then just to prove my point, like Hoffmann elimination, we know it's least substituted, and check out how this double bond is in the least substituted position. Cool. So then first reaction, add all your methyl groups. So CH3, I in excess. And the second, oh, well, I'll just write it out first. Forgot the name of this compound that it makes. Can't remember. There. But it makes nitrogen, this amine, a good leaving group. And so for the second, I just need something to provide me, a base so that I can do that elimination. And so what we've been working with is Ag2O. Put heat. Okay, cool. And so step number 2, all it's going to do is deprotonate my beta carbons and make 2 elimination reactions, but the major product for Hoffmann is the least substituted, as it is here. Okay. This next one. Okay. For these, there's a couple of reactions that you just had to memorize. They didn't really teach us the mechanisms for them. And so this looks very similar to those that we've been learning. So check out how we have a activated benzene ring, and we probably did an acylation somewhere because we're adding a whole acyl group. So we have to, oh, I totally did the wrong one. So we're doing an acylation reaction. And we know that the problem with this reaction right here, if we did a Friedel-Crafts acylation, is this nitrogen that would act as a base, and there would be a whole reaction with only this nitrogen right here. Like there would not be anything added if we did an acyl reaction immediately as our first step. So what we have to do is we have to do a protecting group. And for our protecting group, I'm just going to use an acid chloride, an AlCl3. So the first reaction is like if we're doing a Friedel-Crafts, but it's only going to react with our amine part. And boom, boom. For step 2, we took care of the amine already. Hold on. We took care of our amine. It's an amide now, something that's not very reactive. And so what we're going to do is do another Friedel-Crafts reaction, because now we can do our desired reaction without worrying about anything else getting in the way. So I'm going to do another acylation. And I'm adding a total of 1, 2, 3 carbons. So I'm just going to do another acid chloride with 3 carbons on it. Okay. Remember these lone pairs on this nitrogen, they're donating to my benzene ring. It's an electron donating group. And so wherever we add our acylation, it's going to be in the ortho or para position. So here in this case, it's in the para, so it's telling you where, but I just wanted to give a little like background on what's happening, because I know some of your professors are actually going to have like one of those final exams where you have to go back on different concepts. So that's what's happening here. All right. So for the last reaction, the only thing that's different between these two is I have an acyl group, an amide right here, and an amine in the other one. So all I'm going to do is hydrolyze to get the protecting group off. H3O plus. H3O plus. As we usually remove protecting groups. Cool. I'm going to do this next one. This one was one of the ones that I was getting confused on. So here is where we have electron donating group, right? Never mind, forget what I said. We're trying to make a diazonium salt so that we're able to add on to this benzene ring with an electron donating group. So what we're going to do first, like our first reaction, is to make the diazonium salt. And so we know that we need to use NaNO2HCl. So with that, I make my diazonium salt. Whoa. And I can write the rest of my reaction or of my reagent using what we have in the product. So notice how we have this whole benzene ring with an electron donating group. I'm just going to write that whole benzene ring with an electron donating group as one of our reagents. Doesn't have to be too complicated. And then remember, this is an electron donating group. It's donating electron density and activating the benzene ring. So it's allowing for something to break the aromaticity, but bring it back because it's an activated benzene ring. And so that's exactly what this is doing right here. It's adding to this benzene ring. And the only reason it can is because of this electron donating group. And then we'll talk about that more because we have, I think, one more synthesis problem that has to do with just that. Let me see it. Okay. And I guess I'll skip to that question because that we were just working on it. So this is also on the page that I provided for you guys. This is the synthesis problem. And so again, let me show you the notes that I have on this. Okay. So these are just the basic notes. I have a benzene ring with Y, and Y represents electron donating groups, which activate the benzene ring. Okay, and as usual, what we've been talking about, the diazonium salts, that's what I'm going to be reacting it with. Then notice how the benzene ring with the electron donating group is going to be directing your diazonium salt. So again, it's an electron donating group, so ortho-para. So I'm just going to put it in the para position where it has the least steric hindrance. It was bad, but whatever. Ooh, okay, sure. Okay, and so on one of the reactants, you can only have electron donating groups, whereas on the diazonium salt, it's a diazonium salt. You can add whatever you want to it. Just make sure that on your diazonium salt, if you have electron withdrawing groups, make them be on the diazonium salt, not on the benzene ring with your electron donating group. So let's try out this next one. For this synthesis, I'm asking you to provide the reagent as normal. And so what I'm going to do first is I'm going to identify my electron donating groups or electron withdrawing groups. And so on this benzene ring, I have an electron donating group. Right here, electron withdrawing. Right here, electron withdrawing. Okay, cool. So then again, you separate both of your reagents. One of them has to be a benzene ring with an electron donating group. This is your activated benzene ring. This is what I'm going to do right here. So that means that when you're deciding where does my N2 plus go on the left one, on the left benzene ring, or on the right one, make sure that it goes on the right one with all the electron withdrawing groups. N2 plus Cl minus. And put all your substituents. N2. Okay, cool. For this next one, the same thing, identify all your groups. So electron donating. So this is going to be its own reagent. A benzene ring with 2 electron donating groups. H, H. And so the benzene ring on the left is going to be the one with the diazonium salt. N2 plus Cl minus. Cool. Okay, now I'm going to go back to those other synthesis problems. This last synthesis problem. Okay, yeah. Okay, so for this one, it's one of the weird reactions that we have to learn. These reactions down here, where you use your diazonium salt and add a couple of reagents in order to add things to the benzene ring. And so the first thing that you want to do is make the diazonium salt. And so we know that we can only make the diazonium salt out of the amine groups, not this nitro group. Nitro group? I think it's nitro group, right? So then how I make this a regular primary amine is I'm going to hydrogenate. Let me go back to this to make sure. I'm good. Yeah. So we're going to use H2PDC to hydrogenate and make this primary amine. Oops. Step number 2 is when we make the salt. So as usual, NaNO2 using HCl. That's when I make my salts right here. N2 plus Cl minus. And the last reaction, we don't have any groups on any of our carbons, so what we're probably going to be doing is one of those hydrogen groups where it just becomes a phenol, the benzene ring again. So it's going to be the H3PO2 reaction. So this H3PO2 reaction, it's just going to put a hydrogen in place of my diazonium salt. So I'll just draw it up here. Hydrogen. And so this reaction is cool because you go from something being substituted to taking off this little group. Yeah, so this is something that was hard to do at one point, and they figured it out. It's kind of cool. So that's what these reactions are. These are just ones that you memorize. They didn't really teach us the mechanism for these, so I'm just going to give you the reagents to make each one of these, and I'm going to give you the names of the products because I know some of your professors don't draw the problem out for you, and instead they say like the names of everything. So knowing the names of everything would be helpful. For this one, it's adding the OH group. It's just H2O. So it becomes phenol. So you go from your diazonium salt to a phenol. Phenol. There you go. This bottom one, we're adding a chlorine group. So I'm going to use copper chloride. Copper chloride. And so you make chlorobenzene. There we go. This one you're adding it's called a fluorine group. I can't remember. HBF or something? Let me check this one. Yeah. HBF4. HBF4 to make fluorobenzene. Let me make sure I spell this right. Don't make fun of me if I don't spell it right. It's fluorobenzene. Okay. This is the last one. You're adding iodine. Iodide. Sure. And I'm going to be using NaI, or you can also use potassium iodide. Sodium iodide or potassium iodide. And you're going to make benzonitrile. Oh, I got confused. Okay. Hold on. You're using this to add the iodine. You're going to make iodobenzene. Benzene. Oh, okay. here is where we use is where we're adding the cyano group. So you use copper, so bad at naming, with the cyano group. And then I'm gonna make benzonitro. Okay, cool. For this last one, it's the same one as we were doing in the beginning. So it's H3PO2. Yeah, in order to just add your hydrogen right here. So benzene. So yes, this was like 20 points on my test. So just memorize these for your 20 points. But you're also going to be given a roadmap. So that's another 20 points. So be practicing your roadmaps too. That's 40 points in your test. Just memorizing and, I mean, doing your roadmap is hard, but try. 40 points. Okay. This next one, these are hard too. So rank the following amines in order of basicity. So I didn't put one being the most or whatever, but we're going to do one being the most basic and 5 being the least. Okay, so I'm looking at all of these, and the first thing I see is all my aromatic rings. So this is aromatic benzene ring, aromatic, and this one's aromatic but in a different way. So in this aromatic ring, I notice how my nitrogen and its electron pair is donating to the aromaticity in this ring. So this is an aromatic ring, and this is donating to aromaticity. So when you are basic, you want to grab onto a proton, but if this were to grab onto a proton, it would break aromaticity. It would only have 4 pi electrons, and you would not fulfill Huckel's law, Huckel's rule. And so this is very acidic, and this is not basic at all. So I'm going to put that this is the least basic amine. 5. And I didn't include it in here, but if you were to find, if this were another one of your answer choices, so it'd be like 6 being the least basic or something, since there's 6 of them now. This is an amide. This is going to be your least basic. This is not reactive whatsoever. So if there was a 6, this would be 6. It would go even before aromaticity. This would be your least basic. That was just a side note because I didn't include it. But for this problem, the aromaticity one is going to be number 5. And so let's check. Let me charge my computer. For these next couple of ones, you would notice how some of them are very similar to each other. And so what I'm going to be doing is I'm going to be comparing the similar ones that I gave you. So I gave you one with just regular ammonia, and I gave you something similar with R groups around it, right? So that's the first thing I'm going to compare. I'm going to compare these two to each other and these two to each other. The first one I'm going to do is this one over here on the right. You need to know a couple of the pKa's to answer these questions. So one of the basic pKa's that we know is the NH4+. And the reason I'm writing NH4+ instead of looking at NH3 is because we're talking about basicity. So basicity. And so we know that basicity is inversely related to acidity. So if my acid is strong, then my base is weak. If my base is strong, then my acid is weak. So I'm going to be comparing all of these by thinking of their conjugate acids. So then if this were to grab onto a proton, like something that basic would be doing, like grabbing onto a proton, I'd get ammonium. And so we know the pKa for ammonium, yeah, is 9.4. Cool. So I'm just gonna leave that one here. pKa 9.4. pKa of its conjugate acid is 9.4. And so I'm gonna go on to D. The only difference between E and D is that I have R groups around this one right here. And so we know that carbon is electropositive and likes to push electron density into the nitrogen. So how I like to think of it is if you have like an electron cloud, something small is just trying to catch onto a proton, right? This electron cloud is trying to grab onto a proton. If I have something that's electropositive pushing electron density over here, it makes this cloud bigger and it makes it easier to grab onto a proton. It's like a little net or something. And so we know that if we have two things pushing electron density onto my nitrogen, I have a big cloud right here that's able to catch on to protons. And we know that something that's basic likes to grab onto protons. So it's more basic than something like this. So then I can say that my pKa is greater than the conjugate acid of this one right here, 9.4. Cool. Again, we're talking about conjugate acids for these. Okay. So then I'll move on to B and C because I'm just kind of ranking it in my brain right now. So first thing I notice is that my amines have electron donating groups. So this is an electron donating group right here and the electron donating group right here. The only difference between them is this one is donating electron density through resonance. And this one, like how we were saying, is an R group that's pushing electron density through the inductive effect. So we know that this electron withdrawing group is weaker in comparison to this one right here. Okay, so how are we gonna do this? Okay, so when we're figuring out this question, we again remember how we need to memorize some of our pKa's. So the pKa that we have to memorize for this type of question when we're comparing these two is the one for aniline. So the pKa for aniline is 4.6. There you go. So we need to compare these to each other. We have both electron donating groups, so we know that our pKa's are going to be higher because something is pushing electron density onto this nitrogen. It's making the electron cloud bigger, making the nitrogen more able to grab onto a proton. So the pKa's of the conjugate acids for these, if this has a hydrogen, for the conjugate acid of this one, is going to be higher. So pKa higher than 4.6. For this one as well, pKa higher than 4.6. But in comparison to each other, since this electron donating group is pushing more electron density into this nitrogen, making this a lot bigger, this little cloud a lot bigger, easier for this nitrogen to grab onto a proton, it's more basic. That means our pKa is a little bit higher than this one right here. Okay. So now I got the baseline things for everything, and I'm going to start numbering. So I'm asking you for the most basic. Something that's basic has a high pKa. Okay. So for my highest pKa's, I see B's and B's are higher than 4.6, right? So then it's, for basicity, I'm going to have to rank one. I'm going to have to rank either D or E as number one. And so I'm already telling you this pKa is higher. So this is going to be my most basic. This one's a little bit lower. Number two. So we have 1, 2, and we have this one right here. We need 3 and 4 now. And so here again, this is what's going to give away the answer. This pKa is going to be a little bigger than this pKa right here, the conjugate acid. And so this will tell me that this one is more basic right here. So I'm going to make this one number 3. And this one is a little bit less basic. Okay. And this will be our order. Let me check if I'm good. 1, 2, 3, 4, 5. Okay, that's good. Yeah, okay, so all of these, I think these acidity and basicity questions are a lot more complicated, more concept related, because you have to keep a lot of things in mind. The fact that acidity and basicity is inverse, the fact that you have to use conjugate acid to figure out these questions. You have to memorize the pKs. So write all of your notes down in order to answer a question like this, because these are a lot of thinking. Okay, this one over here isn't too bad. So our last basicity question, and I want to show you a little graph that was made about the increasing basicity. So if you want to memorize this, go ahead, but it's kind of hard when you're dealing with two things that are kind of the same. You have two electron donating groups, so this is not going to be too efficient for differentiating between those two, but it's still helpful for this kind of question right here. So let me show you. Increasing basicity, the most basic one that I'm going to have is let's see, alkylamines are usually your more basic ones. And I'm going to put ammonia. Aromatic heterocyclic things, so with the nitrogen being included. I'll show you examples of each of these. Heterocyclic with your nitrogen donating electron aromaticity, and your amides are the least basic. So I'll give you examples of all these. Amides look like this. The least basic. Heterocyclic that contributes to aromaticity looks like this. I believe this is pyrrole, I think. I'm not sure. For this next one, I'm gonna use pyridine because this one is 1, 2, 3, 4, 5. This one is aromatic without using any of the lone pairs on my nitrogen. So if this grabs onto proton, it won't break aromaticity and we're good. So it's more basic than something that is aromaticity, has aromaticity. Aryl amines. I know I have it written out somewhere, so I'll show you now. Let's see. Can't remember for the life of it. Oh yeah. Okay, that's like aniline. So this is an aryl amine. So it's not being included in your aromatic compound. It's outside, so it doesn't contribute aromaticity, but it's still there. And then last one, or not last one, ammonia, NH3, and then alkylamines that donate electron density and make it more basic. So those are all examples and things that you can memorize, but again, it's hard to differentiate between something that's so similar. So these are both aryl amines, and you would have to differentiate which one is more basic. And if you just memorize this chart and try to answer it, it won't be very helpful. But for this question, it's so right here I have an alkylamine. Right here, I'm just gonna, I forgot to draw hydrogen. So this lone pair right here is donating to electron density. It fulfills Hückel's law, so it can resonate and everything. It's part of the p orbital. And so I'm gonna say that this right here is donating, or is contributing to aromaticity. Whereas this one right here is not. It's a heterocyclic, a normal one that doesn't contribute. Heterocyclic. Okay, but just by like what we said previously, this nitrogen right here in its lone pairs is donating electron dense, or I'm sorry, it's contributing to the aromaticity of this ring. And so if it grabs onto a proton, it breaks aromaticity. So it's not very basic because it doesn't want to break aromaticity. So this is my least basic. My alkylamines, that's one that we can just remember. It's donating electron density because my R groups are electropositive, so it makes the little cloud bigger and it easier for this nitrogen to grab onto a proton. So this is my most basic. And then heterocyclic that doesn't contribute to aromaticity is going to be my intermediate one, so number 2. Yeah, so for this question right here, this little chart was helpful. For this one up here, this is like where you have to apply everything that you know about basicity and acidity and everything. But yeah, we're done with this worksheet right here. If you have any questions, you can send them in the group me and I can work them out on Zoom again and post videos. This is all for part 1. And I'll make sure to post part 2 in a little bit. Yeah.